On this edition of Celebrating Science, a special panel discussion about the physics of information. Brought to you by Canada's Perimeter Institute for Theoretical Physics, an independent, non-profit scientific research and education outreach organization, home to a growing cluster of international scientists who contemplate and calculate new ideas about the very essence of space, time, matter, and information. Perimeter Institute also offers a wide array of educational outreach activities for students, teachers, and members of the general public in order to share the joys of scientific research, discovery, and innovation. In tonight's edition, recorded for radio, 4 noted scientists take part in a panel discussion on the fundamental essence of information and how it applies to some of the most complex questions in modern physics.
Good evening, ladies and gentlemen. Welcome to Perimeter Institute's public event series. My name is John Matlock. I'm a director with the Institute, and it's my pleasure to welcome you here and to all of the audiences who are tuning us in around the globe electronically. We have a very special presentation on the physics of information. We have a special format, special host. He is Bob MacDonald of Quirks and Quarks. Bob is one of Canada's best-known science journalists. He's not only been the host of Quirks since 1992, he has an extensive history in communicating science. This includes his broadcasts on CBC Radio Ideas, As It Happens, and Morningside. On CBC Television, Bob was the host of the children's program Wonderstruck, and we continue to see him on The National, where he is the national science correspondent. In addition to his work with CBC, TV Ontario, and other broadcasters, Bob has written for the Globe and Mail and has written several popular books. He's received several honors for his contributions in science communication, including having received the Michael Smith Award for Science Promotion from NSERC, the Sanford Fleming Medal from the Royal Canadian Institute, and the McNeil Medal for the Public Awareness of Science program from the Royal Society of Canada. He also holds a number of honorary degrees from Laurentian, the University of Guelph, and Carleton. Ladies and gentlemen, please welcome to Perimeter Institute's stage, Bob MacDonald.
Good evening, ladies and gentlemen. Wow. I'm Bob MacDonald, host of Quirks and Quarks, our national science program on CBC Radio. Perhaps you've heard of it. I'd like to welcome you to this very special Perimeter Institute presentation. This evening's discussion is called The Physics of Information, What the Universe Doesn't Want You to Know. And let me begin by introducing our very distinguished panel. On my far left, Dr. Chris Fuchs, a long-term visitor at Perimeter Institute who specializes in quantum information and quantum foundations, and he's also an adjunct professor of physics at the University of New Mexico. Next to him, Dr. Tony Leggett is a professor of physics at the University of Illinois and the 2003 Nobel laureate in physics for his work on superfluidity. He also is a member of Perimeter Institute's Scientific Advisory Committee, and more recently he was named the Mike and Ophelia Lazaridis Distinguished Research Chair at the University of Waterloo. On my right, your left, Dr. Seth Lloyd, a quantum computer engineer and a professor of mechanical engineering at the Massachusetts Institute of Technology, and Dr. Leonard Susskind, a professor of physics at Stanford University and associate faculty member at Perimeter Institute. Ladies and gentlemen, this is your panel for this evening. Now, if you've attended other Perimeter Institute events like this, or occasionally listened to Quirks and Quarks, you know something that most people have figured out. Physicists are not like the rest of us. Oh, I know, they look like normal human beings, but they don't see the world the same way that we do. Take information, for example. When you or I have a question, what do? We look it up. You go to a book, you go to the internet, you ask somebody. The information is just data that's out there. All you have to do is find it, or maybe share it with someone else. But that's not how physicists view information. They want to know what the information itself is actually made of. So imagine you're looking up information on a website. Now to you or I, we just see the details that are on the screen. But suppose you could look inside your computer with a really powerful microscope. Now you see the actual bits of data moving through the wires and the circuit boards. They're individual kernels of information. And these bits are being manipulated, and they're being transferred here and there as tiny little electric charges. Or you can look at an apple. Not the kind you type on, but the kind you eat. You might take a bite out of that apple, and you'll see a bite. But a physicist sees a bit. Or millions of bits. And those bits define the apple, its shape, its color, its texture, its very existence can be defined as bits of information. So this idea that information and physics are intimately related has involved some of the world's greatest scientists in long-running intellectual debates. And their ideas on the physicality of information provide deep, though controversial, insights into some of the hardest problems in modern physics, including our understanding of the universe, one of the smaller problems we have, black holes, and paradoxes that you find in quantum mechanics. Their research is also leading to new technologies to calculate, to store, to transmit information in quantum computing, quantum cryptography, and quantum teleportation. Beam me up, Scotty. So let's get down to the nitty-gritty and see what information we can glean from our guest today. And I'd like to start with Dr. Seth Lloyd from MIT. Now, most of us see information as something that you just read or you copy or you share with somebody else. What's that got to do with physics?
Well, everything. Sorry, did you want a longer answer than that?
A little longer. This isn't the news.
Sorry. So Bob, actually, 150 years ago, people weren't so concerned about information because they weren't living through an information processing revolution. But 150 years ago, a bunch of physicists, James Clerk Maxwell at Cambridge and Edinburgh, Ludwig Boltzmann in Vienna, Josiah Willard Gibbs at Yale, they actually discovered the fundamental formula that describes information. And they didn't describe it in terms of bits. They discovered that formula because they were looking at how atoms move around. And they wanted to quantify this funky stuff called entropy. Now, entropy was at that time known as a quantity that gummed up the works of heat engines, of steam engines, and kept them from doing the amount of work you'd want them to do. But phrased in modern terms, what Maxwell, Boltzmann, and Gibbs discovered was that entropy is actually information. It's bits. So these atoms, as they move around, they carry bits of information with them. And every time two atoms collide, those bits flip. So in fact, not only does information have everything to do with physics, but physicists actually discovered it to begin with.
And it could also be what, now we have light that's carrying information, like fiber optics. So it could be a quantity of light as well.
Yeah, so if you want to see, if you were looking at how the information processing revolution came about, it's because scientists and engineers figured, oh, everything's already got this information associated with it. Let's use it. You know, a particle of light, a photon, it can have a bit of information, like if it's wiggling back and forth like this. So if I take, my Ray-Bans, I put it like this, photon wiggling back and forth like that, you can call that a 0. Photon wiggling back and forth like this, Ray-Bans like that, you can call it a 1. So all these, particles, physical entities have information associated with them. And when we build things like quantum computers, all we're doing is just taking advantage of that.
So does that mean then that information is limited by the laws of physics?
Darn tootin'.
Another precise answer there.
Wow.
Let me turn to Chris Fuchs.
Sure.
From Perimeter Institute. Can you give me an example of how the laws of physics allow us to do things with information?
Oh, well, I certainly can. But I think, actually, just to follow up on Seth first.
Okay.
I've got to tell you about the first time I saw Seth Lloyd in public. He was emphasizing at that time not that everything can carry information, but that everything could be used to compute. And to make this dramatic, I remember him pulling off his shoe and putting it on the overhead projector and saying, you could even use this old shoe to compute. So when he says these things, he's serious about it. So what was your question?
Well, I guess an example, a little beyond the shoe, of how you could use the laws of physics to manipulate information. Or do new things with it.
Well, you can certainly do new things when one takes into account quantum mechanics in So how shall I say? Here's a lovely example. It's something called quantum cryptography. The task that's set in front of two people, Alice and Bob, is that they'd like to share a secret. They'd like to communicate to each other privately. In the classical world, where there was no connection, at least no seen connection between physics and information, when they would send messages back and forth between each other, somebody could gather information and it has no effect on the carriers of the information. Well, in the quantum world, there seems to be a deep connection between the properties of things and the information that one can get about them. So for instance, if you get information about something, it changes the system in the process. This leaves a trace. Alice and Bob can see this trace and they can learn whether someone has listened in on their conversations. So that's one example.
Okay. Now, Dr. Susskind, how do you define information?
Well, I think I would call information everything that you need to know about a system to know what happens next. So, for example, if you had a bathtub full of hot water, what information do you need to know in order to know whether to get into that bathtub or not? Well, you need to know its temperature, you may need to know its volume, to know if there's enough water there and so forth. But that's a very limited amount of information. There's an enormous amount of information stored in the position and velocity of every single molecule in the water. If you really want to know exactly what's going to happen next, you need to know the position and velocity of every single molecule in that water. So there's an enormous amount of hidden information that you don't ordinarily see when you look at the bathtub full of water. That hidden information, the information that you can't see, is what's called entropy. And if you really want to know in detail what will happen next from any given initial starting point, you need to know all of the information, which means everything that can be known, all the numbers, all the velocities, all the positions, which are the maximum amount that you can ever know about that bathtub full of water. And if you knew it, you could predict what will happen next. That's what I call information.
Now, how close are we? I mean, that sounds to me like a huge amount of information. How close are we to actually knowing that? Just in a bathtub full of water.
Well, usually when I get into the bathtub, I know the temperature and the volume, and that's about it.
So the physics doesn't seem to be playing a lot.
Right. Right. There's an enormous amount of hidden information that you can't see, and it goes under the name of entropy.
Okay. But I want a definition here, the difference between what we think of as classic physics and quantum physics.
Yes.
Okay, so.
Yes. I think in principle it really is the same thing, but I'm afraid that to give you the sharp distinctions between classical and quantum, I would have to give you a course in quantum mechanics.
We don't have time
for that. No, we don't have time for that. So I would suggest that you come to my evening course at Stanford, which we call Quantum Mechanics for Old People. And about as many people here come once a week to find out what quantum mechanics is. It's also on the internet.
Okay, but in general terms, as I understand it, in classical physics, you're talking about gross motions, like Newton's laws, push something in action, reaction. With quantum, I think of the very small, what's going on within the atom, within the very tiny world where things don't behave the way they do out here.
Yeah, the character of quantum information is a little bit different than the character of classical information. It's a little more coarse-grained. In some sense, it's not quite as detailed. The uncertainty principle prevents you from knowing all the things that one would think one could know classically. So it takes a little bit less information in a certain sense to know what the quantum state is doing. On the other hand, it again corresponds to knowing the enormous amount of microscopic information that's in that bathtub full of water.
Okay. Let's bring Tony Leggett from University of Illinois into this discussion. How do you define information?
I think fairly similarly to what Dr. Susskind has done. As far as I'm concerned, information always has to be about something, and it has to be embodied in something. And so I think a typical example of useful information is a map. A map represents certain properties of, let us say, a city. generally speaking, it does not represent all the properties, but it represents those properties that you want to know about at any particular time, and it represents it according to a particular scheme. In this case, it represents it on a two-dimensional sheet of paper. We can imagine that in future, and this may intersect with some things come up later in this discussion, we may actually in future have three-dimensional holographic maps, I would think, but right now at least most of our maps are two-dimensional on sheets of paper. So I think every example of information has this character. It has to be about something in the world. It's got to be engraved or embedded in something in the world. But of course the way in which it's embedded may differ enormously. Presumably the fact that I'm talking in Waterloo this evening is something I'm conscious of. Presumably it's embedded in certain neurons of my brain. I don't think, as far as I know at least, we have right now much idea of how exactly it's, as it were, engraved there. If indeed engraved is the right word, it may be a totally misleading word. It may be embodied in more abstract things like rhythms of my brain and so forth. I think we just don't know. But I think it always does have to be embodied in some physical object. And I think there's a famous statement by Rolf Landauer which says that information is physical, and I take that to mean that it has to be, you don't get your information free, it's always got to be embodied in something.
I think a better thing that Landauer could have said is information carriers are physical. I think
Yes.
that would capture your
Well,
point.
it would, yes.
Dr. Susskind?
Yeah, let me completely disagree with you.
I was almost
Not at all.
getting it.
Let's just clarify a point. For example, the information that Waterloo is north, is it, of Kitchener? Or is it south? I don't
Yes,
remember.
north.
But that information is not
Kind of.
contained on the map. That information is contained in Waterloo and Kitchener. Your map and my map might actually be different, and we don't know that until we look at the maps. And all the information on the map is that my map says that Waterloo is north of Kitchener, and your map may say something different. The actual information about the fact that Waterloo is north of Kitchener is contained out there on the surface of the Earth, where Waterloo and Kitchener are.
Is there any information that's not physical?
No,
None.
Yes.
no. Oh, yes.
Oh, yeah?
You know, there's a lovely phrase I like by one of the inventors of Bayesian probability theory, who says probabilities do not exist. And by that he meant to capture the idea that there's a distinction between the world as it is. There's Kitchener and there's Waterloo. And you don't even have to say the word information to put one north and one south. You can just say there's Kitchener and there's Waterloo. And then there's what someone knows about it. Oh, God, I can't remember whether Kitchener is south of Waterloo or east of Waterloo. And you look on a map, or you actually look at the things and you get surprised. And then because you're getting surprised, you're getting information. So just like the probabilist said, probability does not exist. That means it's not out in the world. I would say information's not out in the world. It's in your head.
Ooh,
The
okay.
stuff out in the world's out in the world.
So let me just try to summarize what we've heard so far. And this is hurting me to do this. Because information can be little packets of electricity or quanta light that you can measure that we move from here to there. It can be in everything, including a shoe. It can be classical in the gross sense, or it can be in infinitesimal detail in the quantum world, where you may or may not know all of it, but you can predict the results if you try, maybe. Or it might be a map that's arranged in some configuration that you can try to push your way through. Is that generally what we've said so far?
Yes.
Thank you. Okay, sure. Okay, so let's move into what we can do with information. And Dr. Lloyd, I understand you were actually a consultant for the movie The Matrix.
No, for the movie The Physics of the Matrix. It was
No.
about...
Physics. You're right, the physics of the Matrix.
There you go.
Okay. And you were also on my show on Quirks and Quarks talking about your book, Programming the Universe. So,
Kind of you to mention it.
so is the universe really like the Matrix, a giant computer program that we're actually living in?
Do you want the short answer or the long answer?
Medium would do well here.
Okay.
Yeah.
All right. So I'll have to average them. Well, the short answer, of course, is yes. I mean, it was established 150 years ago that everything contains information, and that every atom has bits around. Every time they collide, these bits are flipping. This table, this glass of water, this shoe, yeah. They're just full of information, and they're processing it right and left. I guess it's a boot. So, yeah. So, the short answer is yes. But then, if you actually want to, but that's something that's really not very controversial. The time to object to that was around 1900, and people failed to. So that's pretty well established.
But what do you mean when the universe is a computer?
Yeah. So there's more. You can say, okay, it's processing information at its most microscopic levels. Therefore, it is a computer. That's good enough for me. But you might also want to know, okay, the universe is a computer. Why isn't it running Windows? Well, maybe it is.
Windows
Yeah.
14 billion.
Well, I would prefer if it ran Linux, actually. That would be. I'm more an open source person for this. But in fact, now we actually know the universe can do stuff like that, because my colleagues and I, for now more than 12 years, have been building quantum computers where we actually build computers that store bits of information on individual atoms. One atom, one bit, to paraphrase the U.S. Supreme Court, at least for the moment. So, yeah, so we can actually build them, and indeed, everything out there that we look at, when we look at it close enough, it's computing.
Well, give me an example of a universal computation.
What the universe is.
What's the universe computing? Like, give me an example.
Oh, well, it's computing itself. It's computing you, for one thing.
Is the answer 42?
You gave it away.
Of course we know the answer. I want to know the calculation.
Yeah.
But what do you mean by that?
Well, so you could think, if you want to think of the universe as a computer, and as I say, it's a scientific fact. It's not really a metaphor. Then the universe is computing everything that we see. This table is being computed by the microscopic motions of these atoms. Lenny's bath that got him warm and clean for this evening. That was the result of that computation. So everything that we see is a result of this computation.
So you're saying just because things are happening, atoms are spinning and molecules are jiggling and planets are orbiting stars, that's a computation?
Bits are flipping.
Bits are flipping.
They can all be described in terms of how bits flip.
What's the rest of the panel think of that?
What would be an example of a process which is not a computation?
Yeah, good question.
Maybe let me take a shot at this too. Maybe 150 years ago, people might have said the universe is a clockwork mechanism. What is the idea that the universe is a computation have that old idea doesn't have?
Well, yeah, it has the idea of information built into it. I mean, of course, you could easily accuse me, as I think you vaguely are, of saying, oh, well, we're in the midst of this information processing revolution. I own computers. I actually build quantum computers. Therefore, I think the world is a quantum computer, right? That's a perfectly reasonable accusation. That's why I was at pains to point out that this discovery that the universe is at bottom processing information was actually made by a bunch of people like Maxwell, Boltzmann, and Gibbs, who had no notion of computation at all. Yet they inadvertently almost discovered the fundamental laws of information theory.
But could you pose the whole idea without saying the word information? Could you say the universe is evolving according to some dynamical laws? It's doing it deterministically. It's doing it reversibly.
Well, yeah, absolutely.
Could you do that without saying the word information?
Yeah, you could do that.
Then what does information add?
Well, so you could also say your computer is just evolving by a set of dynamical laws, or for that matter, your brain is just evolving by some set of dynamical laws, and no information is being processed. But I'm not going to say that, because that would be
insulting. Well, sure, the universe is a computer. Anytime a system evolves according to a set of mathematical laws and goes from one state to the next according to any kind of mathematical laws, you can say it's doing a computation. What is the software? The software is the laws of physics. What is the hardware? The hardware is matter, the things that things are made out of. But, you know, there are some things that a computer may not share with the universe. For example, I have no idea if there's a programmer. I have no idea if there is a purpose to the computations. Most computations have purposes. I don't really think, although I don't know, that there's somebody waiting around for the computer to do its computation, waiting for the answer. Another interesting question is it ordinary computers, you can change the software. You can change the software, you can stop the computation, change the software, and have it do something else. As far as I know, there is no evidence that it's possible to change the software of the universe. So there are some elements which are really, really absent, or at least I think they're absent, from the universe that we would ordinarily think of as part of a computer. I'm not sure there's any good sense in which there are well-defined circuit elements, well-defined switches localized in space at definite positions, which switch on and off the way they do in a computer. In fact, I think there are good reasons, and we'll come to them, I think, to think that that's not the case. So, yes, there are elements of being a computer, and no, there are elements in which it's not a computer.
Or there could be other universes running different programs.
And there could be other universes running different programs. But I don't think anybody's going to stick their finger into our universe and suddenly change the software. Or at least there's no evidence that that will ever happen. So in that sense, it is different than a computer.
You mean you're saying that our universe is unlikely to crash at any moment?
Oh, no. Oh, no. No, no. It's very likely to crash, I think. I think my president has almost guaranteed that.
Well, I've also heard the universe defined in musical terms, the harmony of the sphere, the music of the spheres, and that there are harmonics out there that you could describe in musical terms. But Dr. Soskin, you have another idea that instead of it being a computer, you have the idea that perhaps the universe is a hologram. Tell me about that.
Well, first of all, you say I have another idea. This is a mainstream idea in physics. This is an idea that many, many people have contributed to. And is now a very, very robust idea in physics. It's practically a tool of physics. You want me to say what it means?
Yes,
Do you want me to begin by saying what a hologram is?
Sure. I think of it as a three-dimensional picture that you get on a film, and it's 3D.
It's a technique of storing three-dimensional information on a two-dimensional surface. Short answer. We've learned from black holes, from black hole physics, that the information that falls into a black hole is really, in some other sense, stored on the surface of the black hole, on the horizon of a black hole. The number of bits of information that can be stored in the black hole is no larger than the area of the surface of the black hole. And so in some way, everything that falls into a black hole, the full volume and all of the detail inside the black hole is completely coded by what you can think of metaphorically as a hologram stretched out on the horizon of the black hole. Now, interestingly enough, you can remove the black hole, and you can simply think about, for example, the space in this room. Think about all the people sitting there. Everybody is composed of some bits. The rest of the room is composed of the bits. If you ask how many bits can this room store, you might think that the number of bits that the room can store is proportional to the volume, the number of cubic whatever it is that describe the volume of the room. But in fact, what we've learned from thinking about black holes and horizons is the capacity of this room to hold information is proportional to the surface area of the walls. So it's almost as though the capacity to describe the information in this room was described by a hologram composed out of a film on the surface of the room, the walls of the room. But then if you go out and look carefully at the walls, you won't find any hologram there, because the walls of the room are part of a bigger system, namely the building. And so if you think a little further, you'll say, oh, the information in this room is stored on the walls of the building. But then if you go a little further, well, I don't know what comes after the building. The
planet.
The planet and so forth. But the main fact is that the maximum amount of information that's stored in a volume of space is somehow proportional to the area of the boundaries of the region. And that suggests that in some funny kind of way, perhaps metaphorically, the universe or regions of space are described, roughly speaking, as holograms. Holograms that can change with time, and so things can move around, and quantum holograms, but holograms.
Wow. Oh, but as I understand black holes, they keep drawing more and more material into them, so can you overload that information? What happens if you put more information on it?
No, that's the interesting point. It's taken a long time to sort that out, and it's been a big fight in physics, but it's finally sorted out. And the answer is no, you can't overload it. You can't overload it because the black hole also radiates. So the more information you throw in, if you wait, that information will come back out, and you can't overload it beyond the entropy of the black hole. The entropy is the maximum amount that black hole can hold.
Okay. I guess black holes can also get bigger too, can't they?
Yeah, they can get bigger, but if they're bigger, their entropy increases and their information increases.
So then are you saying that it's possible that the entire information of our whole universe is in a hologram around the outside of our known universe?
Well, I think when we start really talking about the whole universe, we get beyond what we really understand. But, right, we do get beyond what we really understand. But that having been said, yes.
Thank you. Dr. Leggett, we haven't heard from you. What do you think of these two ideas of the universe as a computer and the universe as a hologram?
Well, I think I would ask the question, if you say the universe is a computer and you then say that has to be so because every physical process is basically a computation, and then I want to know what you're excluding. What would it be like for something not to be a computation? And what has one added in that case by saying that it is a computation? And I think I do rather agree with the points that Dr. Siskin raised about the very specific differences. The fact that you can't just put in a new with a humanly constructed computer. The whole point is that you can put in lots and lots of different tapes or whatever, or you put in different things on the keyboard, and it'll run completely different processes. As far as we know, there's no such option in our universe, as you can see.
Now, I want to stay with you to get back to this difference between what we think of as classical physics and quantum. And there's the classic paradox of Schrodinger's cat. Can you just tell me a bit about that and how it fits in?
Okay. Right. So it's very well established at the level in experiments which have been done for many years now at the level of single atoms and electrons that when, for example, a given atom can take two paths and then eventually get to the same point, all the evidence is that it doesn't look as if every individual atom chooses one path or the other. How do we know that? Well, we can basically argue that if each atom did choose one path or the other, then crudely speaking, the number of particles which got to the final point would be equal to the number which got there when they could only go by one path, and the number which got there when they could only go by another path. However, we find that's not the case. And in fact, very spectacularly, we find that when we can certainly sometimes set things up so that we open one path, a certain number, a non-zero number of atoms arrive at a given point here. We shut that path and open the other path, again, a certain number of atoms arrive there. But when we open both the paths simultaneously, no atoms get there. So that seems to be saying that, well, the one thing what you say positively about that is perhaps a matter of taste. However, one can make certainly a fairly strong negative statement and say it does not seem to be the case that each individual atom went by one path or the other. And that's, in some sense, that's the raw experimental facts and minimal interpretation of them.
Okay, that's indecisiveness in atoms. In a way.
Yes.
Okay, but how does Schrodinger's cat?
So, well, we believe, we have fairly firm confidence that the formalism of quantum mechanics describes that situation. And the way it describes it is by associating something called a wave function or probability amplitude with each of these two paths. And then the important point amplitudes is that they can be positive or negative. Actually, a little more complicated than that, but for our purposes, they can be positive or negative. So you can get, for example, the positive amplitude coming through this path, a negative one coming through this path. The total amplitude then to get there will be 0. And that's the way we explain this phenomenon. Now, as I say, we've got a lot of confidence that the formulas of quantum mechanics works at that kind of level. But now, if we believe that everyday matter, tables, Geiger counters, cats, etc., are made up of atoms and electrons and so forth, then they too should obey, at first sight, the laws of quantum mechanics. And then it turns out, and this was a point made by Schrödinger in a very famous paper more than 70 years ago, it turns out actually engineer a situation where if you believe quantum mechanics, the appropriate description of the world is that you have a probability amplitude for a cat. So you have a cat inside a closed box, and you engineer things that at a particular time there's a probability amplitude, non-zero, for her to be dead, and a probability amplitude for her to be alive. And then the question is, how do you interpret that? I mean, at the microscopic level, whenever you had this kind of situation, you could not say each atom went through one way or the other. In this case, can you say each cat is definitely alive or dead at this stage? And this is where perhaps the most furious argument in the whole of the foundations of physics breaks out. People disagree furiously about whether you're allowed to say each individual cat is alive or dead. And I personally believe that if you really take quantum mechanics seriously and you consistently interpret it in the same way at this level as you did at the level of atoms, then you can't.
Now, why is that significant?
Why is that significant?
Why is that important?
Well, because, I mean, look, the Animal Protection Society is very luckily have prevented us from doing this experiment in a statistically significant way. Very few of us doubt that if we were to do it, and we had a whole box of 100 cats, 100 boxes each containing the appropriate cat, and we'd set this up properly. Then I think all of us believe that whenever we took the lid off box number 97, that particular cat would very definitely be either dead or alive. In fact, we don't really like even to see her in an indeterminate state. So, in other words, we have a very great difficulty in reconciling the interpretation of the quantum formalism, which we're used to giving at the microscopic level, with our sort of common sense experience at macroscopic level, the everyday level. Okay, so in other words, because you can't look in the box, at the time when you don't know, the cat could be either alive or dead, and you're calling that's itself a sort of a state of being. Well, it could be both. It's not that it could be either alive or dead. It is, in some sense, neither alive nor dead. Just as the atom is not true to say that the atom went through one path or the other. Okay.
There's nothing particularly unusual about the idea that there's a box in which a cat may be either alive or dead.
No, absolutely not. No.
So this is not the whole story. The whole story has something to do with, as you know better than anybody, with something called coherence. And roughly speaking, I would say what's implied here is that you can do something called an interference experiment, which, and it's very hard to describe, but I think one could say, oh boy, I don't know how to describe her coherence. Maybe you can give it a shot, but you know, you have not said the whole thing when you just said there's a box that could have a cat, which is either alive or dead.
But can I take you up on that? Yeah. Okay. Indeed, the phenomenon of interference is fundamental. How do we know at the atomic level that it is not true that an atom went through one path or the other? Right. Because precisely of that phenomenon of interference, which in the simple example I gave said that get a finite number coming by one path, a finite coming by another path. When both paths are open, nothing. That's a particular example, destructive interference. But what I want to get at though is how does this uncertainty or this dual existence possibility have to do with information, which is what we're really talking about tonight? Oh, well, I think I would turn that over perhaps to, for example, Chris. Because I think that
Yeah, let me,
You won the Nobel Prize.
He's smart. He knows when to quit.
this will demonstrate why I'll never get a Nobel Prize.
But, I mean, if I were to give you my resolution of the problem, a bit strongly heretical,
Okay.
one which I suspect none of my three colleagues here tonight really share, which is that I think that the whole of the Schrodinger's cat paradox rests on an implicit assumption, which is a very, very natural implicit assumption. It's one we make unthinkingly every day of our lives, practically, and it's this. If you have a theory, I mean, big things are made of little things, crudely speaking. Okay? So if you have a theory which describes excellently the behaviour of little things, then it should describe excellently, at least in principle, the behaviour of the big things made of them. That may not be true. That would be my solution to the problem. A solution perhaps ought to come in quotes, but so I say that's heretical. It's very heretical.
Okay. So, folks, how do you relate this to information?
Sure, for a completely different answer. So there's this mathematics called quantum mechanics. I mean, there's a physical theory, and it has mathematical terms in it. And among those mathematical terms is one called the quantum state. People talk about the quantum states of things. And for instance, Tony was talking about the quantum state of a cat. One possible quantum state for the cat is alive. Another possible quantum state for a cat is dead. And when one has this paradoxical issue with the cat in the box, one writes down a new quantum state that is alive plus dead. And the issue is, what the hell is that? Now, if one thinks of quantum states as states of reality, in other words, when you write down this thing called alive, it means the cat is alive. I mean, and the cat's alive regardless of me. And if you write down dead, it's dead. It's dead regardless of me. If you think that those mathematical terms correspond to properties of the cat, that it can be alive or that it can be dead, you run into troubles. Where information comes in is with the realization, at least for the belief of some physicists, that these mathematical objects don't represent states of reality, but represent states of information. So when one writes down alive, it means, oh, I can predict that when I open the door, I see the thing alive. If one writes down dead, it means, I predict that when I open the door, I see it dead. And when one writes down alive plus dead, one is predicting still something else. One is predicting if you open the door and look to see whether it's alive or dead, you'll get that answer. But you can also predict that you would see other things called interference, like Professor Susskind was talking about, with more complicated apparatuses, not just our eyes and opening a shutter, but you surround the box with some interesting equipment like Seth Lloyd is talking about, a big quantum computer, and you can see these other things. And that's where information comes in.
The ironic thing is that indeed we are now doing experiments building quantum computers using superconducting circuits, using an idea that Tony, that you proposed, that is what is called macroscopic quantum coherence, in which a zero is represented by a gajillion electrons going around a superconducting loop this way, and a 1 is represented by the same gajillion electrons going around the loop this way. And we can, with some difficulty, but not that much difficulty now, create a state of these gajillion electrons where they're going around both ways at once. So they're effectively instantiating this Schrodinger's cat.
And you could not only create it, but actually verify, crudely speaking, that's what you've got, right?
Right, exactly. You can demonstrate exactly the kind of interference that Leonard was asking us to demonstrate. And in fact, do things like quantum computations, do funky algorithms, take several of these things, entangle them together. So it's interesting. I guess the question is, you were suggesting that maybe macroscopic things don't behave in the same way. But now we have things that are more and more macroscopic, actually following up on your own suggestion, right? Demonstrating experimentally your own suggestion, things that are more and more macroscopic that are being dead and alive at the same time.
But if you're saying that, the little things, as you say, and the physics there don't match the physics of the big things, then what about this whole effort to try to come up with this grand unification theory that brings everything all together, if what you're saying is right? Doesn't that prevent that from happening?
I think in the usual technical sense of grand unification, it wouldn't have any major impact there, because you're, as I understand it at least, you are dealing there with attempts to unify different theories of elementary particles. You're only talking about, in some sense, a rather few elementary particles at a time. However, it would have very substantial, I mean, if what I said does turn out to be right at some stage, then it would have very substantial impact on certain ideas about applying quantum mechanics to the universe as a whole.
Yeah.
Yeah, let me try to say it a slightly different way. There's a thing called the uncertainty principle about particles. In principle, it should apply not to just the single, small, tiny elementary particles, but to baseballs and everything else. Now, it's very hard to test, but if you had a baseball, because of the uncertainty principle, there's certain limits on predictability, and in particular, those limits on predictability follow from quantum mechanics. If you believe that quantum mechanics applies to baseballs, if you believe that you can use the rules of quantum mechanics as the standard quantum mechanics requires, I think Tony would say quantum mechanics possibly may really break down. The rules may really break down for studying baseballs, and that's an experimental thing that can be tested, and it has never, ever been tested for large systems. Quantum mechanics has never been tested for objects bigger than, I'm not sure how big, but I'm not sure what the largest system that's ever been tested for. And so it's perfectly appropriate. It's a really mainstream question. Will the rules of quantum mechanics apply when applied to objects much bigger than it's been applied to now? And nobody knows the answer. But what I would say is I think there's some circumstantial evidence that it would. And the circumstantial evidence is that it's very hard to isolate breakdowns of quantum mechanics. You say in looking at grand unification theories that you're looking at very small number of particles, but in fact those small particles contain virtual particles, and the virtual particles contain other virtual particles, and eventually you're talking about a lot of particles of very small size and very heavy mass. And the fact that quantum mechanics applies to that is some kind of indirect evidence that it might apply even to complex systems. Now, I would be the first to admit that's a weak argument, but a weak argument in the sense you better go and test it directly anyway.
Okay, I want to get on to a topic that I'm interested in, which is one of the weirdness aspects of the quantum world. Dr. Lloyd, tell me about teleportation.
Oh, teleportation? You mean as in beam me up, Scott?
Well, whatever your definition of it is.
Yeah, so there was a book, it might be out of print, called The Physics of Star Trek.
By Dr. Lawrence Krauss.
That's right, by Larry Krauss. And in the original version of this book, he investigated the possibility of performing teleportation. You know, can I step into a little booth here, be dematerialized, the bits of information that get measured here are sent somewhere else, and then I'm rematerialized over there. Actually, it looks like I got rematerialized into a left-handed universe from a right-handed to left-handed here.
Either that or a fly.
Well, I mean, yes, the other thing, of course, like the other thing that typically happens is the process goes awry, and you're left with, you know, the good Kirk and the evil Kirk, and somehow they have to be merged. That's also, you know, it's kind of Schrodinger's cat-like, actually, now that I think about it. So now Larry Krauss pointed out that really you couldn't do this, because if what you imagine just taking a measurement and you measure the state of this system right here, you can get a lot of bits. You know, for a typical human being, you'd get something like 10 to the 30 bits out of this human being. That's about how many bits are required to describe a human being. But you would at the same time destroy the state of this human being, and you would not learn all sorts of features about its state, because quantum mechanical measurement on its own is both destructive and incomplete. You can't tell everything about the system. And so that says, well, you shouldn't volunteer to go through a teleportation experiment, because when you come out, you will be quite different from when you went in. You'll be not the same at all. But then about 10 or 12 years ago now, a bunch of researchers, Charlie Bennett is the first person on the paper, Gilles Broussard, some other people, it's a long number of people, figured out that actually you could teleport things from one place to another. And the secret if you can imagine this, is to make sure that your measurement actually reveals no information about the system you're trying to teleport. Instead, what you do is you set up this kind of funky quantum correlation called entanglement, where you have two entangled systems over here, an entangled system over here, and an entangled system over there. Entanglement is a form of correlation. Correlation just means two things get information about each other. In quantum mechanics, things can have more information about each other than they have any right to have. That's entanglement. You set up two of these systems that have more information than they have any right to have. You make a measurement over here along the system that you want to teleport together with this half of the entangled stuff. And that information reveals no evidence, no information about what the system was. It doesn't indicate it was Captain Kirk or Q or Dr. Spock. But when you send it over there, that information is enough to transform the other entangled stuff back into Kirk. So in fact, these are, it was a remarkable and shocking result, because I think that anybody who knew about quantum mechanics said you can't possibly teleport things. But in fact, it turned out to be possible in not only in principle, but actually in practice, because now a number of teleportation experiments have actually been performed.
What did they actually teleport?
Not me.
I didn't think so.
Well, the people have teleported photons typically, like individual photon polarizations. And may I say, they don't do it with very high fidelity. Like if you had your favorite photon, I wouldn't recommend handing it over to these people here.
So one photon, that's a long way from a Captain Kirk.
Maybe 7 or 8 photons. Now, we're also trying to teleport. At the moment, we have an experiment to try to teleport one rubidium atom from one place to another.
Okay. And how far can you teleport?
Well, you can do it for many meters. Actually, in fact, since you can distribute entanglement over long distances, kilometers or more, there's no reason why you shouldn't be able to teleport things over very long distances. But again, I wouldn't volunteer to be the first person to do it.
You're very wise. Dr. Susskind.
Well, okay. The word teleportation is a rather charged word, and I think maybe it's less than meets the eye. Teleportation does not involve exceeding the speed of light. Sure. It does not involve moving things from one place to another place with faster than the speed of light. In fact, as far as I can tell logically, at a logical level, there's no difference between teleportation and just moving a thing from one place, moving a thing from one place to another. And that's not surprising that you can move some information from one place to another. I don't see the big difference.
So then what's the big deal? The
big deal, I think, is that you can do it for very microscopic systems, and maybe that you can send them with the speed of light, but not much less, but not faster than the speed of light.
Well, I can do that with a radio wave. We're broadcasting this program with the speed of light.
Yeah.
A lot of information.
I would have to disagree with that slightly, Leonard, in the sense that well, first of all, what you say is correct, right? At bottom, teleportation is getting from here to there.
But then you shouldn't disagree with it.
But on the surface of it, it's actually incorrect. And if you go to a deeper level, like at the superstring level, it seems to be incorrect as well.
Well, here was what was considered a big deal at the time when it was found. These things called quantum states are parameterized by real numbers. So that means, maybe in a way that Seth would describe it, it takes an infinite amount of information to specify a quantum state. And in this teleportation process, when one performs the measurement that he was talking about that reveals no details about the system that's being teleported, what he meant by that was it reveals no information about the real numbers that are required to specify it. And so it was found that by performing a measurement that revealed 2 bits of information, you could get this quantum state that's parameterized by an infinite amount of information.
Yeah, so what I say
from one place to another.
What I say is weird is that the information you send from one place to another, if you just look at that information, it wouldn't tell you anything at all of what's being teleported. And yet you can combine it with this other half of this entangled state at the far end and use it to recreate the original thing in its entirety. So it's a rather strange situation in that you're not actually sending, at no point are you actually sending information which on its own allows you to recreate this thing. So, I mean, the purpose at the end, for successful teleportation, right, is to get the thing from here to there.
Mm-hmm. Which you can do in other ways.
Yeah.
But there's another thing which is very interesting, which has to do with quantum information, which is worth talking about also. It has to do with duplicating information. You can take a page of information. Here's a page in front of me that has some information on it. And I can faithfully reproduce it on a Xerox machine. At least I think I can faithfully reproduce it on a Xerox machine, but it's only classical information. In quantum mechanics, it's very interesting that you cannot clone information. You cannot take a thing and faithfully reproduce two versions of it simultaneously. This is one of the most interesting things about quantum information, the impossibility of duplicating an object. That I think you will find will not get undone by some clever experimenter.
No.
Okay, let's bring this home with what we can do with this information, with our understanding of information as quantum bits, as teleportation, as how we can move it from here to there. What are we going to get out of this? You mentioned quantum computers. I mean, what is there any way that we can come out of the theoretical and into the practical with this?
Well, I think, okay, so the way I came to start thinking about the universe as a computer was I was taking little pieces of the universe, you know, collections of atoms, and figuring out how to make them compute. And then I said to myself, well, what's going on here? They're actually computing already. All we're doing in the laboratory is hacking into this computation to make them compute in a way that's different. And here I actually have to take a exception to something you said before about our inability to program the universe. You made a metaphor where the laws of physics are the program for the computer. And well, I think that, you know, we're physicists here. Actually, I'm now a mechanical engineer, but I'm trained as a physicist. So we tend to be physics-centric. But it's not just the laws of physics, it's also the laws of chemistry and the laws of biology. And then when you started looking at all these laws, it's basically the program is any bit of information that can make a difference about how the universe behaves. And it's not so strange to think of, for instance, programming a biological system. In fact, you know, genetics does it. That's what sex is about, right? Sex is about creating newly programmed biological systems. And I don't think you'd object to that form of programming the universe, would you?
I'm almost 68 years old. I don't give a damn.
Time for a new program, yes. But I just want to ask our panel generally, just what do you see as we're in the information age. What's the future of the information age? Dr. Fuchs?
What's the future of the information age? I think Tony should take that question.
Well, I could talk a little, I think, about what one could do with specifically our understanding of information in a quantum mechanical context, because I think that for many, many years, it was the sort of standard belief in the physics community that the weird phenomena which we associate with quantum mechanics were forever going to be confined to the level of single atoms or pairs of atoms and so on and so forth. However, in recent years, and particularly in the last 8 or 9 years, we've really gone very far beyond that. Seth was describing some of the experiments he's involved in where you actually see interference between these states of a reasonably macroscopic, that is everyday level, ring in which billions of electrons are circulating one way or the other. Many people ahead of time said that was simply impossible, it couldn't be done. It has been done now, and I think therefore we should be a lot more sanguine about the prospects of being able to observe these very subtle quantum effects in other systems where previously it was thought totally impossible. For example, certain types of biological system. I think it's at least on the cards that within the next few decades we will, for example, be able to see interference between the different conformational states of the rhodopsin, which is the first stage of human vision, and so forth. So I think that's one direction, at least.
Tony, I'm just curious. Suppose it turns out that I'm not sure what you think one way or the other, but supposing it does turn out that quantum mechanics does fail for these large systems, do you think that means that quantum computers, large-scale quantum computers, are impossible?
I think that would very much depend on how exactly it failed. if it were to, I should say instead, as perhaps a mildly amusing matter of history, that when I and a few other people started thinking seriously 25 years ago about the possibility of seeing the kind of interference effects which Seth is now seeing, at least one of my motivations at least, was precisely the hope that we might not see them. That, in other words, we would find that by the time we got to this kind of level, quantum mechanics has failed. Well, disappointingly, it hasn't, and that's conceivable. That's because in some sense, the systems we're looking at, very sophisticated as they may be from an engineering point of view and so forth, from a conceptual point of view, in some sense, is still rather crude, in the sense that you've got all your electrons are basically locked together. They're described by a single variable, and you're just interfering different values of that variable. There are lots much more sophisticated kinds of interference experiment we could do in principle, and if, for example, it turned out that in technical terms, a very highly entangled state automatically generated a failure of quantum mechanics, I think that could be the death knell for quantum computing. But certainly, as Dr. Siskin has said, there's absolutely no evidence right now that that's going to happen.
Well, this is something of a joke, but I think it's relevant to this. It likely depends upon, if there is a deviation from quantum mechanics, this issue of whether you can build a quantum computer is likely dependent upon what the deviation looks like. One of the crucial things in the technological development of quantum computation is to be able to do error correction. And for this, error correcting codes have been developed. I think I first heard this from Michael Nielsen, who's in the audience, but he speculated that if quantum mechanics fails, then perhaps we could just error correct that problem away.
That's funny.
And do quantum computation
That's funny
anyway.
because you error correct by making the system even bigger.
Even bigger.
Yep, that's right.
And you might expect that would make it even worse.
It might or it might not. I think it depends upon what this deviation looks like. If the deviation makes it look like, well, it would get technical here, but I could say things about trace preserving.
There's a very
maps.
beautiful example that was very recently discovered in biology. It had been speculated for more than 80 years that photosynthesis might involve quantum coherence on a large scale. And photosynthetic molecules, they're huge. They have thousands and thousands of atoms, and they involve, a photon comes in, it gets absorbed. Actually, it gets absorbed not in one place in this molecule, but in a quantum superposition of many places. And now there's strong experimental evidence that actually this quantum coherence between all of these thousands of atoms in these photosynthetic centers is actually responsible for transferring that energy from where the photon is absorbed to where it can be turned into chemical energy. All the more remarkable because this is the sort of process where up till now we've only seen it at a few thousandths of a degree above absolute zero, and these are processes that are taking place at room temperature.
It always astounds me how you physicists, if you have a problem, you don't understand it, you just add something to make it work. You add another dimension, We
call that, we add BS, that's what we call it.
Yeah. In other words, we don't know, and so we'll just keep going anyway, even though we don't really know. Well, I'd like to open this up to our audience now. If you have questions for the panel, we have microphones on each aisle, and I invite you to come up to the front, and I'm going to ask that you only ask one question. And please make it a question, not a speech. And please say whether you want to direct to a particular panel member or the panel in general. So do we have any questions from the audience? Any questions from the audience? While we're waiting for the audience, I have one for the panel. Whenever you're talking about all this stuff about uncertainties and about maybe it's this, maybe it's that, what are the chances you're wrong? That everything we know is wrong.
99%.
I would say the chances are 100% that we're wrong about parts of some things. And I think it's probably close to 100% that we're not wrong about other things. And the problem is we don't know which.
That's great. Yes, sir, we have a question.
Hi. I guess I'll ask generally to the panel. Since we've been talking about information, I thought I would ask a question to try to clarify in my mind what information is. I think at one point we talked about information as being something physical that's described by physics, which led me to think if I had a notebook that I took my pen out and scribbled till my pen was empty. I had added some matter and some energy perhaps to the notebook. But then if I took that same notebook and wrote, let's say, prime numbers in it until my pen was empty, I feel like I added something different. What is that I just added in physical terms?
Well, it's for a very long time in human history, the idea of information had to do with meaning, right? Information was something that was about something, it meant something. And it seems to me you're trying to get at this distinction there. Now, one of the most remarkable advances in starting to build computers and to build communication systems like fiber optic cables was made by Claude Shannon at the mid part of the 20th century. He realized that you could talk about quantity of information and information being processed irrespective of the meaning of that information. So for instance, it's the cable guy's, his job is to come and get your house so that you can get, a megabyte of information per second in there, and it doesn't matter if that megabyte is Shakespeare or if it's pornography, right? His job is to just get that megabyte in there. So now you're very rightly saying some information means a lot more than others. Not that, there's a lot of useless and meaningless information out there. In fact, watching cable TV is a good way to find this. But it's actually very important for the theory of computation and information theory that you don't have to talk about meaning to talk about quantities of information and amounts of information processing.
But wasn't that also an example, though, of the difference between the information which is in your mind and the carrier of that information, which is the paper?
Is that what you're trying to get at there? Or?
Sure.
Ms. Eskin, what do you think of it?
Well, I think that the difference is very real, and in some sense, the information in your mind is information about neurons, information about the particular configuration of your brain at an instant of time, and the information on the piece of paper is information about the ink drops on the piece of paper, and they're completely different bits of information. They may, however, be correlated. There may be connections between them, between those two different kinds of information. The correlations might be interesting. In a sane, coherent person, there'll be good, strong correlations between what's on the paper and what's on his brain. In a maniac, there may be no correlation whatever. So they are very different, they're different things, but they may be correlated to each other.
But that correlation would be a thought. And yet, they think of a thought.
The correlation would be a physical correlation between one set of bits and another set of bits. A physical correlation in the physicist's sense of correlation.
Not sure what you mean. Because he can leave the paper in his desk.
Correlation means that if you measure one thing, that influences what you would get if you measured another thing. So, if you come along with an experiment, a psychology experiment, and you write something down on a piece of paper, and somebody looks at that piece of paper, then you can do an experiment and ask what is the correlation between what's in the person's head. You ask him, what's on that piece of paper? I wrote down on that piece of paper that King Canute had warts on his nose. And now I ask somebody, what does that piece of paper say? And he says, King Canute had warts on it. Then the correlation has been faithfully established, but it's a correlation between two different collections of bits, not the same information. On the other hand, to show that it's not the same information, you could go take somebody who's insane and say, what does that piece of paper say? And he might say, Bob McDonald has warts on his nose. And therefore he got the correlation wrong. So,
okay.
Yeah.
Okay. Thank you very much. Question here.
Yeah, this is for Dr. Leonard Susskind or anybody else who cares to answer. One of the things that you said was that there's no evidence that there's a programmer or an outside source, mucking around with the laws of physics or the software of the universe, and or at least we haven't observed any. Now, this reminds me of like a video game. So
this is what
reminds me of sort of a video game. Let's say your character's in the video game, right? And the player doesn't like the outcome and decides to reboot the game or reload it. And we as characters in the game, how would we ever possibly observe that somebody's mucking around with our system? So I'm curious, that raised the thought in my mind. How would you be able to observe such a change if it did occur?
Yeah. No, I get the point. The point is well taken. That if you change the rules, start over again, how would anybody know that the rules were changed? One way you might notice that the rules were changed is that if you suddenly made a change, you might discover that history was inconsistent. That you come along and you suddenly change rules, and you might discover that what you thought were the oldest, most primitive dinosaur bones are found, instead of at the deepest level, they're found in the highest level of geological strata. Just because somebody came and changed some rules in midstream. And in that sense, you might find that what you thought were the laws of physics might not reflect themselves in what you would have ordinarily expected the historical record to reproduce.
Very good. Okay, thank you very much. Yes, sir.
My question is about if information can be without relation to any objective matter. Talking about information in our mind, there is a theory out there, it's called holonomic brain theory from Carl Pribram, which tells that information exists as a spectrum inside your brain rather than attached to exact neuron or something. So my question is, can information be present independent of a matter or... Yeah, that's my question.
Okay. Can the information just exist and then we sort of discover it? Is that the idea? Okay.
Yeah. No. Tony made the point in his early spiel on what he means by information, that information has to be about something. The very definition, information should be about something. Now, part of the discussion, we haven't quite gotten in that direction yet, but I think perhaps the most interesting thing to come out of the existence of the world being quantum mechanical rather than classical, is that we've discovered that the information is not what it used to be about. When one talked about the position and momentum of a particle and said one has information about it, one had information about what was actually there. In the quantum world, it seems that the information is not about what's actually there, but rather what comes about from an interaction. So people talk about these things called quantum measurements, and if one says a quantum state is information, well, it's information about something, and that something is what will come about from the measurement interaction. So information is always about something. It's not just disembodied stuff out there like energy.
Thank you very much. Yes, sir, on this side.
Oh, okay. So, my question is, if it is true that we cannot duplicate information or a system of information at the quantum level, isn't it meaningless to predict anything, since the process of prediction is to express something that we know and say that it's a duplication of reality, or is everything we know just approximations?
So there's actually, when the no cloning theorem of quantum mechanics says that you can't take a bit of information, a quantum bit of information, in an unknown state and then make an exact copy of it. There's no procedure that will do that. But you can certainly take a bit that's in a known state and make a copy. Or even if you know if the bit, for instance, is electron spinning this way or spinning that way, you can create another electron that's spinning the same direction as the first electron. It's merely if the electron is in some unknown quantum superposition of being spinning up or spinning down, there's no procedure that will allow you to make a copy.
Yeah.
So you can certainly have deterministic behavior and make copies of certain types of information. You just can't go the whole hog and copy the whole quantum bit.
Yeah, let me say it a different way. You can't make a universal quantum cloner. You can't make a machine that will reproduce a configuration no matter what state it's in. But you can certainly make a machine, for example, that will reproduce up electrons or electrons at some particular location in space. So you can do repeated experiments to continuously reproduce electrons at the same point in space, but the machine that you make for that will not also be able to reproduce electrons which happen to be in with definite momentum. So you can't make a universal cloner. That's, I think, the right statement.
Maybe that's why there's only one universe. We just can't duplicate it, Ken. Could never make another one.
Maybe.
Thank you very much. Yes, sir. Yes, sir.
This is for the panel in general about the hologram idea. Now, I know Dr. Susskind said you can't generalize the results from the black hole for the entire universe, but I just wanted some speculation on how the topology or the shape of the universe could, I guess, change its information content, or also if we believe that the universe is expanding, does that mean its surface area is expanding and it can hold more information in the future?
Yeah. I think the answer is yes, that it can hold more information because the surface area is expanding. But I will tell you this, let me just say it this way. This is one of the main questions that people like myself are struggling now and a little bit confused about. It is one of those questions that if I were to give almost any answer, the probability would be about 50% that I would be wrong. The application of the fundamental principles of quantum mechanics, the principles of quantum gravity and so forth, to the universe as a whole is really obscure, and we don't understand it. And it is perhaps one of the great and exciting facts of physics, that there's that much out there that we don't understand now. I don't have an answer for your question, a complete answer for it. But I would say come to my seminar on Friday.
Which means you've got a job for a while. We're almost out of time. We'll just take a couple more questions. Yes, sir.
I'm a biologist, so let's have a problem with semantics. If I go back to the bathtub analogy, the temperature, the motion, the energy of each of the molecules, to me is data. That's not information. It's when I take all of that together and decide whether I'm going to burn myself when I step into the bathtub. That to me is information.
Well,
How do you deal with the difference in that terminology between data and information?
Who would like to take
Anyone?
Well, I don't know. I think of data and information as largely being the same thing, as long as the data is about something. I think the physicist's use of data. Now, data doesn't mean data recorded in a notebook. It means data recorded in the molecules of the water in the bathtub. That data is what we do call information.
Perhaps our questioner is asking the difference between information and knowledge. There's information about that.
Information doesn't require the existence of anybody to know about it. You know, a tree that falls in the forest is a piece of information that doesn't require anybody to know about it. The way physicists use information is a very impersonal, non-biological concept, which simply is, as I said, it's everything that specifies. I said everything you need to know, but let me say everything that in principle specifies what will happen next. And certainly we don't normally assume that somebody has to know what it is for it to be a piece of information.
Dr. Folk?
Oh, yeah, that was painful for me. Well, I spent a lot of time at Bell Labs, where Claude Shannon had come from, the man who invented information theory. And the way he worked out the concept, it was based on the idea of surprise. So a good experiment that I could do, for instance, is I could take this piece of paper and I could write a 0 on it. And I think in some of the perhaps loose talk we've been using here today, one would say, well, you've just written a bit on it. But watch this. I know he'll get the right answer. Seth, I'm going to give you this piece of paper, and it has a 0 on it. I give it to him.
Thank you, Chris. Information is teleporting.
Seth, I'm giving you that piece of paper, and it has a 0 on it. How much information did you gain from the paper itself?
None. It's got a 0 on it. I already knew it had a 0 on it.
He already knew that it had a 0 on it.
I would disagree. I would say he found out that there was a 0 on it.
No, he didn't. He already knew it because I told him.
Well, actually, he only knew that you said, well, the information he had was that you said there was a 0 on it. He did not know there was a 0 on it.
And in fact, come to think of it, since we go way back, I actually thought it was going to be a 1 until I
Nevertheless, what's the point of this example? The point of this example is, at least mathematically, the way information is quantified is in terms of the idea of surprise. And so if Seth has some ignorance about what I'm going to give him, then he looks at the thing written on the paper and he says, aha, I gained some information. But that's a function not only of what was on the paper, the actual physical configuration, but it was also a function of what he knew. So I just take point with what Leonard said, that... Leonard. I said Leonard. That in the background there is always this thing, maybe not a person, but someone who writes down probability and has some ignorance.
That's like the two fellows are looking at a flock of sheep, and one of them's a quantum mechanic, and the first fellow says, oh, those sheep have been sheared. And the quantum mechanic says, well, at least half of them, half of their sides have. Don't know about the other side because I can't see it. Okay. Yes, sir.
Following the postulate of the universe as a computer, do you know of any formalized study on what it might be working on?
Operating system?
Yeah. Well, no, actually, so I think there is more of a reason. The simple fact that everything is processing information doesn't mean one shouldn't talk about things in terms of information processing, any more than the fact that everything's made out of superstrings means one shouldn't talk about superstrings, right? You actually get some very interesting predictions about the universe thinking about it as a computer. So one of them is actually you get a kind of a computational picture of the holographic principle, or analog of it, or it's complementary. So the holographic principle says, here's the maximum number of bits you can cram into some volume. That's proportional to the area of the volume. There's a computational version of that that says, what is the maximum number of ops, or of bit flips, that I can cram into some time in a particular volume? And you find out, quite remarkably, that this is also related to an area. It's like the area of a two-dimensional world sheet that goes through the middle of this volume. And I guess the other thing, so I think that there are already in quantum gravity and black hole physics, ideas of information have proved very powerful, and the holographic principle is a particular example of this. But I think we can learn a lot about the universe by thinking of it as a computation. And the best thing about thinking about it as a computation is actually explain something which is quite mysterious. So what something that's very mysterious, at least from the physics perspective, is why is there so much meaningful information in the universe? You know, why aren't we all just like a bunch of like random molecules bouncing around all over the place? Well, if you take something that's computing and it gets programmed at random, you can prove mathematically that it's likely to come up with all sorts of strange and complicated and fascinating patterns. Whereas if you just take the molecules of water in Lenny's bath and look at them, they'll just be jiggling around at random. So in fact, we learn something about why the universe is complex by thinking how it's computing.
And when it's done?
One last question. Yes, sir.
Well, the universe as a computer program seems quite interesting, but I have a question. Like, if the laws of physics, have they changed since the beginning of time? Then that would affect, does that have any effect on the software? And also the completeness theorem, sort of like trying to define the entire sort of universe. You couldn't do that from within, as the computer program.
So that's an excellent question. So the laws of physics don't seem to have changed very much since the Big Bang, though they might be very different in other places in this very big universe of ours. But other kinds of scientific law have changed. For instance, the laws of biology are changing all the time, because the laws of biology are determined by the actual physical biological systems that are out there. And you brought up Gödel's incompleteness theorem. The way that applies to the universe as a whole, actually you can derive this now by looking at the universe as a computer. One of the fascinating features about computation is that you can prove mathematically that if you have a computer and you set it off computing in some way with some program, and you ask almost any question about the far distant future of what that computer is going to do, the answer is you can't know. This is how this incompleteness theorem manifests itself in computers. It's called the halting problem. You can't even know if the computer is going to do anything a long time in the in the future. So what this means for the universe as a whole is that we won't be able to predict the far distant future. The only way to find out what's going to happen is to let it happen and see what happens.
There's a wonderful short story written about the most powerful computer in the universe, and it was asked the ultimate question, is there a God? And the computer says, there is now. I'm afraid that's all the time we have for this evening, but I would like to thank our distinguished panel tonight. Dr. Chris Fruit from the Perimeter Institute, Dr. Tony Leonard, University of Illinois, University of Waterloo, Dr. Seth Lloyd from MIT, Dr. Leonard Tustin from Stanford University.
To learn more about the Institute and to enjoy other programs, visit us online at perimeterinstitute.ca.